Okay, hey, analyzing iOS apps with Strongarm. So first up, Tenon, and I work for this company, Data Theorem and analysis. So the idea here is, say you're Netflix, for example, Data Theorem, some of money is we'll take the Netflix application, and of course we'll tell you, how to fix it. Just fiddling with my slides here. Go ahead and analyze a mobile application, privacy issues, what have you, or to go about this. So, application onto a device, observe what it does, and see if it's called dynamic analysis. And we do also this method of static analysis, dynamic analysis, in which you load, and with static analysis, you don't execute the application file, and then kind of dissect that to see what kind of information you can. Again, this doesn't involve any, so as I mentioned at Data Theorem, myself, I focus primarily on. I'm going to be talking a bit about today. Did want to do this, if you did want to take it apart, of course you're going to need to of that application file. So when someone downloads an app, what they're actually receiving archive file ending in the iPhone package archive. So you can unzip it, look around and been told my audio is chopping, so I'm going to go ahead and see if that helps at all. Any better? Just continue here. Going to contain resources such as, oh wow, let's see, iPhone microphone. For hearing me. I'll refresh. Hey, so I'm just checking if that's any better on the audio. Okay, great. Okay, I've just got a message that the audio is good now, and I just want to check you can still see the slides. Okay, wonderful. thank you for the help to the moderator behind the scenes, and my apologies for the delay there. So as I was explaining, if you want to analyze an application, you need to understand its structure. It's really just a zip file, so you can unzip it and see what's inside. So you're going to see resource files like the app icon, localization files, property lists, as well as compiled executable code. And that compiled code is in a binary format called the Mach-O file format that we'll take a look at. So this is just, if we did unzip an app archive, everything in green is those resource files, icons, string files, localization files, and everything in purple is compiled code that'll be executed when the app runs. So we're going to take a look at a few aspects here. We're going to ask the question, why bother analyzing a Mach-O? What can you find? We'll take a look at the structure of a Mach-O. And then finally, we'll see how this tool, Strongarm, that I made can help with that task. So first up, what are we looking for when we analyze a Mach-O? Well, there's various kind of questions that you can ask and various tools that you can make if you do want to analyze Mach-Os. So the first, of course, is security testing, and that's kind of going to be the main focus. So maybe you want to flag any unsafe or dangerous API usages, or maybe you want to look for statically embedded API keys. Another common use case is optimizing your binary. There's good reason to keep binaries under a size limit because it makes, it's easier for users to download, it takes up less space on their devices. And lastly, you might want to tinker with a binary. You might want to edit it to change its behavior, to unlock, some hidden functionality, what have you. Okay, so taking a look at the structure of a Mach-O. So it's just a file like any other. So just like a JPEG, for example, would have some internal structure specifying, the compressed pixel data that should be rendered into an image. Similarly, a Mach-O is just an organizational tool for structuring the code that's going to be loaded into a process when the operating system wants to run it. So Mach-O is just an organizational tool for code and data. And the way that it's laid out is you have this table of contents at the start of the file, which I haven't visualized here. And then you have a number of segments. And each of these segments is just a container. So each of them will contain a number of sections. But you don't just have segment 1, segment 2, section 1, section 30. Each of these has a special name and purpose. So this is a kind of more real example of segment names and section names. And again, each of these contains something specific. So for example, one of the major things that a Mach-O will contain is a bunch of compiled code. And all of that compiled code goes into the text section within the text segment. So as another example, another important piece of data contained within a Mach-O is strings. And strings are always going to be in the C string section and the CF string section. And if you're curious, C string section stores, well, C strings, as the name would imply, just classic string literals. And CF string contains core foundation strings. So these are things like NS string literals in your source code. They get rendered into this section CF string. So the point being, all of these sections and segments have a specific kind of purpose and contain a specific kind of data. And one difficulty with Mach-O analysis is that this data is highly interconnected. So there's lots of pointers to other pieces of data in the Mach-O. So if you did want to go ahead and analyze a Mach-O, you have to do lots of jumping around and following links to other places and cross-referencing data before you're able to get to any kind of meaningful information. Okay, so going back to the kind of task at hand, say we're looking at the Netflix application, and we want to find calls to some method called doWork. Maybe we've decided doWork is really unsafe and no one should ever use it. Maybe we're just curious how often it's called for performance reasons, optimization reasons. Doesn't matter for now. We just want to find all the places in the compiled application that doWork is called. So before I continue here, it's really important to note, if we had this call in our original Objective-C source code, my class doWork, this is Objective-C message passing syntax, but it's really exactly equivalent to that call I have below. The top form is just syntactic sugar to the bottom form. So when it's compiled, this message send syntax will be compiled into a function call to Objective-C message send. The first argument will be the receiver of the message send. In this case, it's this my class reference. And then the second argument will be the selector that we're sending in the message. In this case, do work. Okay, so keep that in mind. So say we're having a look at some of the code in a disassembler. And I apologize, my animations have gotten a bit messed up here, so we won't have everything fade in nicely, but hopefully that's okay. So we've got this Objective-C message send call, and it has two arguments, the receiver and the selector that's being sent. So the receiver, being the first argument, will be stored in the x0 register, and the selector will be stored in the x1 register. So since we're looking for calls to do work, which is the selector, we want to find the value of x1 when Objective-C message send is called. So we can see this call to Objective-C message send with the arrow next to it, and we're going to want to find the value of x1 when that's going to be executed. And it's these instructions just above it that'll do that. So if you're not, too brushed up on your assembly, that's totally fine. What these three preceding instructions will do is load the 64-bit value at this memory address into the x1 register. Okay, but that obviously raises another question. Well, what's that memory address? What's special about it? What does it do? What's stored there? And note that we're currently in the text segment and the text section as we're looking at code. So if we follow that pointer and see what data is being loaded there, well, that takes us into the Objective-C selector references section in the data segment. And if we look at that 64-bit word, it's another pointer. So we've got to follow another link to somewhere else in the Mach-O. Okay, no problem, we can do that. So we follow the link, and that takes us to the Objective-C method name section in the text segment. And now, thankfully, that's the end of the chain. Here we've got that ASCII literal do work. Okay, so we've done it. We've taken a call site to Objective-C message send, and we've tracked it through a couple of layers of indirection all the way back to the selector name that's being invoked there. Now, this is a simple example, but everything in a Mach-O is like this. Everything has multiple layers of indirection, these structures that reference each other in crisscrossing ways, and it can be quite complicated to kind of yield any meaningful information if you wanted to analyze it, if you wanted to find something out about a binary. So Strongarm is a tool to, kind of help with this. So moving on from the structure of a Mach-O to using this tool, Strongarm, which helps. So Strongarm, as I mentioned, encapsulates all this complicated logic in Mach-O parsing and analysis. So if you've used a disassembler before, Strongarm is essentially a disassembler as a Python library. It's also robust, production grade. We use it heavily at Data Theorem, and it runs against 10,000 apps every day. It scans the entire app store. And it also supports cutting edge features from Apple. So every year, Apple makes changes to the Mach-O format to, decrease binary size, to decrease link and load time, and Strongarm has support for all of these. They generally involve sort of weird changes to the structure of a Mach-O. And Strongarm, I routinely update it to handle those. It's also performant. Give me just a moment. I've just been notified my audio is a bit scratchy. I'm just checking whether I should reload the page. Okay, so I'm just going to quickly reload the page and hope that that fixes it. I'll be right back. All right, thanks for holding, everyone. Let's just speed right through. Okay, so using Strongarm, just a quick example of what this would look like. So firstly, you're going to import some symbols from the Strongarm library, so you could use them, of course. Now we're going to use this Mach-O parser, and we're going to give it a path to the file that we want to parse. After that, we're going to need to get a binary out of that parser. Now, I'm going to skim over the details here because it's not so important. But essentially, Apple lets you package two Mach-Os into the same file. It's the concept called a fat Mach-O. So what this is used for is, say, you could have a single file that contains a 32-bit executable and a 64-bit executable. So the details aren't important, but essentially we're going to ask that parser to give us the 64-bit slice. Okay, we've got our binary. Now lastly, we're going to get a reference to a Mach-O analyzer. So with the binary alone, you can get a lot of useful info, but for some of the things that require a more kind of heavy-duty cross-referencing, you need this Mach-O analyzer object. And now once we have that, we're ready to go. We can immediately start doing interesting analyses on the binary. Here's the most basic example I could think of, just printing the strings. So that's just a function call away, a method call away rather. And you can see all the strings that are referenced within that binary. Okay, so earlier when we talked about why you would bother analyzing a Mach-O, I gave these couple of examples of what you might use this for. So detecting, flagging unsafe API usages, and searching for statically embedded keys and passwords. And I want to show you how you would go about doing this with Strongarm. So for the first example of flagging unsafe API usages, firstly, we're going to do the same thing we did when we took a look a moment ago. We're going to parse our file. We're going to get a 64-bit slice out of it. And then we're going to get a reference to this Mach-O analyzer using that binary. Next up, we can use this Objective-C calls to API to ask the analyzer to give us all of the calls to some API we're interested in. Just as a basic example, I'm flagging usages of UI WebView. Not to pick on UI WebView too much, but it's deprecated. It has security kind of issues. WK WebView has been its modern replacement for many years, so I figured why not. So we're going to look for all the usages to UI WebView in our binary, and we're iterating over them. So for each of these calls, we can print out, we've found a call to UI WebView, and it's at this address. Go analyze further here. And then when we run this, that's it. It's searched through the binary, and it's found all the places where UI WebView init with frame was invoked. And again, we could use more APIs here to follow up and inspect each of these call sites further if we wanted or needed to. Okay, moving on to something a little bit more interesting, finding crypto operations using a static key. So it's worth mentioning, why this is a problem at all, statically embedding a key in your application binary. And the issue is that this is a very kind of low-hanging fruit for security researchers. So if you're statically embedding a key in your binary, it's trivial for an attacker to go and retrieve that key and then gain unauthorized access to whatever system that key is interacting with. So this is one example that I thought was particularly terrifying. This car device statically embedded a key in their mobile application. And by abusing that key, you are able to remotely control the vehicle of anyone who has purchased this device. It's just terrifying. Anyone who bought this thing is compromised because of this statically embedded key. So statically embedded keys, really bad. We don't want them. And we want to detect them. We want to enforce some sort of lint, some kind of analysis, so that we can be sure we're flagging these if they ever pop up, and hopefully embedding this in our pipeline in some way so that this never makes it to production. Okay, so what does this look like? Firstly, we want to identify the crypto operation that we want to inspect. So here I'm going to be looking at common crypto encrypt, a function provided by common crypto. And I'm asking the Mach-O analyzer, okay, give me all the places where ccrypt is invoked. And then we're going to look at each of those to see if the key argument has been statically embedded. We're going to iterate over each of those. And what we're going to want to do is analyze the method implementation where that ccrypt call is used, because we need to look at the context. We need to look at what the argument to ccrypt is going to be. So we use this Strongarm API, Objective-C function analyzer, get function analyzer. We give it a start address for the function. And then once we have a reference to the function, we're able to inspect the x3 register where the static key is going to be passed. So it's the fourth argument to ccrypt. Therefore, it's going to be stored in x3 because arguments go x0, x1, x2, x3. And we're going to use this API, get register contents at instruction. So Strongarm will statically analyze that call site and try to identify, is the value in this register statically known? Is it an immediate value that's statically known? Or is it dynamically generated at runtime? So of course, that's what we want to know as well. So we're going to ask the question, are the contents of the x3 register an immediate value that's known at static analysis time? And if so, we know that this is really bad because we found a ccrypt call that's using a static key. Now, the value of that register, of course, it's not going to be a string because registers can only hold numbers, they can't hold strings. It's instead going to be a pointer to a string, to somewhere else in the Mach-O. So we could go ahead and use this API, read string at address. And then if we run this, you can see we've actually managed to find a ccrypt call with a static key. And you can see there's the static key that we've embedded in our binary. So you could use this sort of code sample either defensively or offensively, searching for statically embedded keys in black box binaries. Okay, I'd like to quickly take you through some other sort of basic Strongarm APIs. Although I've just been noted that my audio is scratchy, I'm going to go ahead and reload the page. Hey everyone, thanks for holding through my slides once again. And yeah, thanks for your issues. Some good questions in the queue, so I'll definitely get to those. And if you do have any questions, please feel free to drop those in the presentation, and I will be very happy to talk about this with you. Strongarm APIs. Something you might commonly want to do, for example, by inserting a load command. So there are you can use for that as well. Oh, okay. Sorry about that. Well, I'll breeze through this. No worries. Strongarm is open to Data Theorem for letting me work on this in the open. And thank you for your time. My apologies. Some audio issues. So security issue, what do we do with it? Well, we know, hey, you found that, we found this, and here's how you fix it. People hire us to find security issues for them. If we have pre-written scripts that identify, we do have pre-written scripts. You can look in this scripts repo implemented with Strongarm. Okay, thank you so much. You know, this was interesting, and I appreciate you bearing with me.